Hello students, and welcome to this video where we're going to talk about the concept of concavity. Concavity is when the direction of the graph is curving either up or down. So we're going to talk about a differentiable function f on an open interval. And we're going to look at something called the second derivative test. If we take the second derivative test and it is greater than 0, meaning, it is positive, then we know that it is concave up on a particular interval. If we take our second second derivative and it is less than 0, then we know that we are going concave down for that particular portion of the function. So this is going to be very, very similar to what we did for increasing and decreasing functions, except that we have to take it one step further and we're going to find our second derivative. So let's say I have the function 2x cubed plus 1. I'm going to start out by finding my first derivative, which is 6x squared in this case. And then I'm going to find my second derivative, which is 12x. Okay? And just as we did before, we want to evaluate that second derivative when it equals 0. So when does this function equal 0 versus when is it undefined? And because it's linear, it's never undefined. And when I solve for x, I actually get 0. Now this point here, we used to call it a critical number. Because we're working with the second derivative, we're no longer going to call it a critical number. Instead, we're going to call it a point of inflection. Big key word. And simply that's a point where the graph changes direction. So basically when the signs of f double prime change. So it's going to be important that as we proceed to our next step that we check to make sure that our signs do in fact change. So just like before, I'm going to create my little number line and I'm going to put all my points of inflections on that number line. And then I'm going to look at these intervals, which are negative infinity to 0 and then 0 to infinity. And I'm going to test a point within the second derivative. Any point within that interval, I'm going to plug it in and evaluate within the second derivative. So I'm going to choose -1 and +1. And when I plug in -1, I end up getting -12. And when I plug in +1, I end up getting +12. And so -12 is a negative value and +12 is a positive value. So I put the respective negative and the positive. And the fact that there is a sign change from negative to positive going around 0 confirms to me that, yeah, this is in fact a point of inflection. If I were to solve this problem and end up with a negative and then another negative, I would have to go back and say, wait, no, that is not representative of a point of inflection. And now I look at those signs and I can say, okay, I know that I am concave down from negative infinity to 0 because I'm concave down whenever the double prime is less than 0. And I am concave up whenever I'm positive going from 0 to infinity. Okay? Now, I do want to let you know that it is possible to find relative extrema using the second derivative test. But because we already learned a method to do so with the first derivative test, I'm actually going to choose to not discuss that. But I did want to make you aware that it was available and is a possibility. And in some courses or some textbooks that you may use, you might see that book utilize the second derivative test for finding relative extrema. But for the purposes of what I like to teach, we only use the second derivative test in order to find our points of inflections as well as where we're concave up and where we are concave down. As always, I hope you found this video helpful. If you need or have any other questions, please don't hesitate to reach out.